We're team number 4. We are doing a G meter with a big hole design. Today we are going to talk about low power embedded system. I'm Shuhan Chen.
Dan Swoboda.
EJ Kohler.
Corey Fox.
Tim Carroll. I'm Carl Anderson.
A little bit overview about what we are going to talk about today is first of all the background and applications, and also the hardware consideration, software consideration, and the power supply. A little bit background for the embedded system is a computer system designed for specific control for functions with real-time computing constants embedded as part of a complete device, including hardware and mechanical part. The motivation of designing a low power embedded system or low power system is, first of all, we got a finite amount of power supply, which considered as a powered by the battery or solar panel or something. Also, it needs a real long standby time, and also it's sometimes you can compensate for the performance, which means you can underclock or just running on low battery consumption mode. Also, with low power consumption, we can generate low heat, and there will be low power loss too. The most obvious examples of nowadays actually the Ultrabook versus the traditional laptop like 3 years ago. The huge difference is actually the battery time. For example, nowadays our Ultrabook can stand up to like 6 to 10 hours, versus traditional laptop 3 years ago can only do like 2 or 3 hours. That's actually because of the solid-state hard drive versus the traditional mechanical hard drive. Although in the traditional laptop, they're still trying to save power by turning off the hard drive sometime, and it still didn't do as good as the solid-state. And also the use of ultra-low power CPU, for example, like the Intel Atom or Core 2U series or the LV series stand for low voltage series. Also the LED screen versus the LCD screen. Also the chipset was designed surrounding with the concept of the ultra-low power concept. Although computer is not real considered as an embedded system, so some example of the embedded system is for example, digital watch is actually, especially like the Casio watch is running on the threshold mode, which is around the threshold of the semiconductor, which can run for months or even a year with just a single tiny battery. Also some automotive application, for example, like most extremely performance car, they will just actually cut off the alternator to generate power for the car, and also consumer electronics, which embedded system, most of them are actually powered by battery now. And for the last year's IEEE conference of the solid state, Intel actually gave a really huge presentation on their near threshold voltage processor and memories, which they claim with the chart, they claim like there will be 5 or 10 times battery efficiency versus either the above threshold voltage processing. And that picture was actually an Intel processor running just by the solar panel. And we are designing a G meter, which is a embedded system because we're doing some calculation with that and the data analysis. And also, we're trying to meet the specification of 30 days standby time.
All right, Tim and I are going to talk about the properties of low power design, which include reducing capacitive load, reducing wasteful activity, supply voltage, and switching frequency. I'm going to start off with the reducing capacitive load. The power in a CMOS circuit is defined as the bias power plus the leakage power plus the short circuit power plus the dynamic power. But the dynamic power takes up about 80 to 90% of that, so that's what we want to focus on. And this is the this is the formula for the power, dynamic power. Capacitance is a variable in that, and one way. And so what dynamic power really is like it's the energy that it takes for the signal in your circuit to go from high to low. We can reduce that, then we can reduce the power. And we can also increase the frequency because it'll take less energy to go from high to low. A way to reduce the capacitance is to reduce the chip size. We know that because capacitance is proportional to area. And we can also reduce the external accesses. They are much more capacitive than the on-chip memory devices. So if it's possible, use on-chip memory devices rather than off-chip. In our project, we actually have an example of when could be a problem. One of our accelerometer is it's consuming much more current than we originally thought because it is like a giant capacitor. So another way to save power is reduce wasteful activity. One way to do that is turn off the clock to unused peripherals and also sleep modes. We're going to utilize some of these an example is that we are going to utilize this by turning off our screen when we're not using it.
All right, I'm going to talk to all you guys about reducing the supply voltage. Nowadays, there's a technique called undervolting, which is used in a lot of applications, such as in your cell phone. It's basically taking a processor, such as a 5-volt processor, and running it at a lower voltage. If you just lower it 44% from 5 volts to 3.3 volts, you'll actually save about 56% of the energy that was consumed before. One of the downfalls of this, though, is when you reduce it from 5 to 3 volts, you also have to reduce the clock frequency, which, as we all know, will then any application that you want to do will then be slower. So companies now have what they call a true 3-volt processor, which will run at the same clock frequency as the 5-volt processor. This very confusing graph right here is a voltage reduction technique. What it basically says is, for our project, we had certain specifications, which I'm sure all of you guys have. And so what we did at first was make sure you get a working prototype. So what this is pretty much saying is, here's the total power consumed on the y-axis. On the x-axis is your performance. So first step is to get all your performance. So you just add hardware to whatever your design is to make sure all your performance is up. And then for your last step, focus on reducing your voltage by adding either more hardware or something else. One of the downfalls of this, though, is there's usually a proportion to the size. So when you add more hardware, the area is going to be larger. So you have to compromise for, is lowering the voltage the easiest way to lower your total power consumption, because then you'll have a greater area.
All right, I'm going to talk a little bit about ways we can use software in our embedded system to reduce power consumption. So I guess sort of two overall architectures of software in embedded systems. There's using a simple control loop. In this case, your processor, your microcontroller, is always active. It's always checking for events to whether events have occurred, calling subroutines to handle different tasks or different functions. So in this scenario, your processor is always active. It's always consuming power. Another sort of main architecture is an interrupt control system. In this architecture, the tasks and functions that have to be performed are triggered by events such as pre-programmed timers or external inputs. So whenever they're triggered, an interrupt is called that executes the necessary code. The architecture that's more conducive to low power designs is the interrupt-driven programming. The microcontroller can be placed in a low power or sleep mode to save power when intensive processing is not required. And then the code that handles specific events or functions or tasks are just triggered by whatever interrupts are programmed. This graph just gives you an idea of how this works. Basically, it shows that for most of the operation, in low power mode, the microcontroller is drawing very low current, and then when interrupts are triggered, the microcontroller is active for very short periods of time, drawing more current, but the overall average current will be very low. And many companies are developing microcontrollers with this application in mind, including several low power modes and efficient interrupt handling. It can be kind of hard to select which company has the best microcontroller. They all claim that theirs is the best. This is a chart comparing the MSP 430 with the from TI with the microchip PIC 24. Like I said, it can be like this is from TI, so their numbers are better, but on the other company's website, they show that theirs is better. But the point is that they all show that they draw very low current in both cases, less than a microamp in their standby loads.
Okay, so Tim mentioned a really interesting design concept, which is to first try to maximize performance and then work backwards from there. That was a funky graph. Work backwards from there to try to reduce power while maintaining as much performance as you can. And a great first place to start when you reach that point in a low power project is the clock system. Today I'm going to be talking specifically about two microcontrollers, the MSP430, which is in TI's low power Launchpad development boards, and also the ATmega 328P, which is the low power variant of the ATmega. It's in a lot of the low power Arduinos. So there's two ways really that you can reduce power used by your clock system. That's first to reduce the frequency of your clocks, and second to just turn them off altogether by putting them in sleep modes. And both these things can be done statically or dynamically. So you can set your processor to be running at a very low speed initially and leave it there, or you can do what many like cell phones and embedded systems like that do, where they vary the speed of the processor over time. So let's start with frequency. Corey began to introduce the fact that a lot of the current that's consumed in a CMOS device is consumed during switching, and so the idea of reducing frequency to minimize power is that by executing less instructions per second, you're having less switching operations, and since voltage is held constant and power is a multiple of voltage and current, you're reducing your power. So there are both software and hardware settable clocks. In the MSP430, there's a digital controlled oscillator or DCO clock where you write 8-bit value to a register, and then the clock runs at that speed. And then in the Arduino boards, it's a little bit different. There's just an 8 megahertz oscillator, and you write to a register to divide by powers of 2, so you can run it at 4 megahertz, 2 megahertz, 1 megahertz, etc. Now there are downsides to these internal oscillators, and the main downside really is the speed of the oscillator tends to be highly variant with changes in supply voltage and in device temperature. And so when you need accurate time, like we do to run a real-time clock for our project, you'll often have to use an external quartz clock oscillator. The problem there is that while you do have a more accurate clock, generally in that application you can't turn it off that much because then you lose your clock signal. What you can do is sleep between events. So let's talk about sleep modes or low power modes. So Carl introduced the idea that a lot of companies try to paint their processors as being the lowest power, and they select metrics that indicate that. And so it can be difficult but also very beneficial to sort through all the different data sheets and the different metrics and figure out what's the best. So I don't need to get really deep into this, but the major concept is that the deeper you go in your sleep mode, the more clock sources and the more peripherals become turned off. So first the CPU goes off, and then the CPU and the peripheral clock goes off, and then all three, and then all four. The downside of going into a deep sleep mode, however, is that it takes a lot longer to wake up. So wake time can be particularly hard to deal with when you want to wake up out of a deep sleep mode, especially in embedded systems that need to respond to highly irregular events that can't be predicted. So my example would be an embedded system that's running the anti-lock brakes in a car. You could imagine that a few extra milliseconds between the point where a sensor detects that a tire is slipping to the point where that computer is working to get that car stopped can really be the difference between danger and safety for the occupants of the car. So you have to be careful using sleep modes with irregular events. But with regular events, you can wake preemptively. So a good example would be like the 3G and 4G standards, which are time multiplexed. So your phone only has to be listening at a very specific window of time that reoccurs at a very regular interval. And so what it can do actually is wake up preemptively so that it's already fully awake when it's time to listen to the signal.
All right, so I'm talking a little bit about batteries. Nowadays we have a lot of wireless devices, and all these are generally powered by batteries. Specifically for our project, we have to power our device on 2 AA batteries and have it last for about 30 days. So to meet that specification, selecting the right battery can really help us out. So I'm going to compare both alkaline and lithium batteries. Both of them have a nominal voltage of about 1.5 volts. Under 500 milliamp constant drain for a AA battery, the alkaline batteries have about 1,800 to 2,600 milliamp hours, while the lithium batteries have about 27 to 3,400 milliamp hours. However, another thing like in design is you're going to need to think about cost. For an alkaline battery, a standard AA battery costs about $1, while a lithium battery costs twice as much. That's just one thing that you need to consider. In addition, alkaline batteries are better for low use devices and low drain devices. These are devices that aren't turned on all the time and don't need to be constantly running. Examples would be like flashlights and remote controls. While on the other hand, lithium batteries are better for high drain devices and devices that need to be running all the time, such as clocks and video equipment, like your smoke detectors in your house need to be running constantly. So those are things to consider. When comparing the alkaline versus lithium batteries, in a low drain performance at about 50 milliamps of constant drain, you see that the alkaline battery lasts about 75% of the length that the lithium battery lasts. So in a low drain performance, it's really, it's almost negligible to pick between the two just because they're so close and the cost is much less for an alkaline battery. But what you can see in this graph is that the lithium battery holds its voltage much better than the alkaline battery, which is one of the reasons why we opted to go with a lithium battery for our project. On the other hand, when you look at the high drain performance, so 1,000 milliamps continuous drain, the lithium battery is going to last you about 3 times as long as the alkaline battery. So here's another graph kind of representing that same sort of thing. When you have a 25 milliamp drain, your alkaline battery is going to last you almost as long as your lithium battery. So it's really more cost effective to just use a lithium battery, maybe use more when you are going to have a slow drain like that. Then on the other hand, you got your high drain 1,000 milliamp continuous, and your lithium battery performs much better than your alkaline battery. So in summary, we talked about backgrounds of low power devices, and we talked about the hardware and software considerations, and then we talked a little bit about the power consumption of multiple low power devices. Any questions?
Thank you. I have a question. So you were talking about the, waking these things up, microcontrollers and put them in a sleep mode. What's the kind of time frames that it takes to wake them up in terms of real time?
Yeah, I mean, like on that chart that I showed, back. Yeah, like so going after. Yeah, so like TI claims that they can start up the car, like basically be fully awake in less than a microsecond. And that's, I don't know exactly if that's true or not, but that's what they claim.
So when you have something drop, I'm just asking now in your project, when something's dropped, how long does that G-force last?
Yeah.
You may not have the answers.
Yeah, I guess we don't exactly know that. I mean, we're taking samples that, like we're sampling off of our accelerometer output, like a lot, like the samples are a lot wider than that. So like there's enough time for it to like wake up and do all the processing in between samples. But as far as like how long an impulse, like one impulse of acceleration lasts, I guess we're not exactly sure yet. But
The accelerometer is like a big capacitor with sliding plates, so it's a capacitive discharge when there's an impulse, and we think that we're going fast enough to catch that discharge.
Are there other questions? If not, let's thank them again.